I'm Sakata, a researcher in the field of technology management. Today I'll discuss society and engineering, and how to bridge the gap between them. The main content focuses on two areas: computational social science, which is my field of expertise, and social entrepreneurship. For the section on social entrepreneurship in the latter half, I'd like you to follow along while applying the content to your own respective fields. Also, since people from many fields are here, I want to avoid diving deeply into one field. And I'll try to keep the discussion broad and general so that it applies to all of you. First, I'll talk a little about my field. As mentioned in the introduction earlier, my studies combine economics and social sciences with an engineering approach, forming a hybrid of the two. The topic I'd like to talk about today is computational social science. The content will be a combination of engineering with social aspects, including but not limited to economics. In terms of my previous experience, for the first half of my career, I worked at METI, where I was in charge of policy making. After that, I moved to academia to focus on teaching and research. The time in each role is now about equal. So you could say my career is a hybrid too. This relates to today's talk, but now I'm involved in policy making on innovation, university reform, and regional revitalization through the lens of a university professor. My areas of expertise are shown in the diagram below. There's computational social science and tech management on the far left. And as the underlying method for those things, we have complex network science. And then on the far right, natural language processing. Recently, I've been conducting research in fields such as LLMs and generative AI. For the first half of this talk, I'd like to touch on computational social science. What kind of academic field is computational social science? It uses data-driven approaches such as data analysis, modeling, and simulations to study human behavior in society, the decisions behind that behavior, interactions between people and organizations, and the social phenomena that arise from such interactions. These are analyzed to discover reproducible patterns. Based on those discovered patterns, we predict future behavior. That's the gist. With the advancement of the digital revolution, the fusion of computational science and social science is progressing. In the past, social science mainly relied on mathematical methods that were relatively small in scale and handled only limited amounts of data. On the other hand, computational science has traditionally been more math-focused. But with the advancement of technology, the two fields have rapidly begun to merge. In particular, in 2009, a well-known paper titled Computational Social Science was published in the journal Science, which many of you may be familiar with. Since this paper was published, this has become the recognized name for the field. It is now possible to collect data and analyze it with unprecedented depth and breadth. With this new capability, I primarily rely on data-driven approach in my work. However, when it comes to discovering valuable patterns or making predictions in the domains we analyze, it's essential to properly understand the social and cultural context, as well as conventions. However, this isn't something that you can understand just by looking at the data. You need to experience it firsthand, study research findings in the humanities and social sciences, and listen to the insight of others. There's a well-known book by Christian Madsberg called Sense-Making. He argues that information without a proper understanding of the surrounding social and cultural context is nothing but thin data, lacking any real meaning. I actually keep this book on my bookshelf where I can always reach it. From the perspective of someone who works with data, the book is full of hard truths from beginning to end. However, I always keep these points in mind while conducting my own research. In that sense, all of you gathered here today probably encounter, to some degree, similar elements in your own academic fields. I hope you value this community that has gathered here today, and by fusing together engineering, information science, or other scientific approaches with humanities and social science approaches, I hope you can use this integrated approach to achieve outstanding research results. This chart here is meant to illustrate what we mean when we talk about social and cultural context. Here, to visualize patterns in the data, we mapped keywords extracted using natural language processing from about 4,600 research papers worldwide that focus on carbon emissions from homes or households. The data is divided by continent, and if you look at Africa, here in the lower middle part of the figure, you can see keywords related to things like cooking, biomass, stove, as well as coal. These are the keywords that stand out in this region. On the other hand, if you look at Asia, those words disappear. Instead, keywords like consumption, future, development, and other keywords related to urbanization and economic growth become more common. Next, if you look at the Americas, which is here on the far left, you can see keywords like gasoline and transportation. This shows that, in the Americas, when it comes to carbon emissions from households, transportation seems to be associated significantly with emissions. And then there's Europe, here in the upper middle part of the figure. In Europe, keywords like green economy, mitigation, and willingness show up. It seems to feature a lot of elegant words. I think this suggests that Europe is a hub for policy concepts where they are widely broadcast. In any case, even looking at the same word or topic of household carbon emissions, when we look across the world, we can see just how differently people think. Or in other words, the topic of focus is not the same. Therefore, without first understanding these differences, trying to analyze the situation in Africa, the Americas, or anywhere else is essentially meaningless. In any case, we can't just look at the data. We also need to consider the cultural and social background and take those contexts into account as we interpret and untangle the findings. This approach is essential in computational social science. Next, I'd like to talk about the types of data that we handle in the context of computational social science. Here, I've listed about 6 examples. As you can see, we also work with soft data, like social media and Amazon review data. On the other hand, as shown on the right, we also work with S&T papers, including research papers, patents, and other technical documents. Regarding social media and Amazon data, Amazon reviews, for example, tend to be relatively short, and the associated attributes are usually limited in number. However, there are a large number of them. Regarding S&T papers, as many of you already know, they are rich in content. They also include attributes such as co-authors, author-assigned keywords, citations, and specialized terminology, among other detailed information. In addition to these datasets, we also have activity-related data on the bottom row. These include social networks, whether that's a network of friends, or, for companies, business relationships. Data concerning networks like these, and the interactions that occur within them, are part of the covered datasets. Then there's human mobility and the use of transportation. And on the far right is innovation activities, which is one of my specialties. Computational social science is a field that deals with a variety of data like this. In my laboratory, we generally work with datasets containing hundreds of thousands of data points or more. As an example, I'd like to talk about human mobility via railroads. This is railroad data in the Kansai region, and this visualization shows the overall passenger flow for those using private railway lines and subway lines. In Kansai, as shown in the diagram, there are IC cards like Pitapa and Ikoka. This is essentially the Kansai version of the Passmo card in Tokyo. The data was provided from the firm that issues these cards. First, I'd like you to take a look at the left side of the figure, which uses light patterns to visualize the movement of people under normal circumstances. On the right side, we have the movement of people on June 18th, 2018. The day when there was a major earthquake in Kansai. Both visualizations show the same time of day and the same day of the week. So by comparing the two, you can clearly see the differences. Let's take a look at what happens. Now it's 5:30 a.m. and you can see that the trains have started to move. Past 6 a.m., you can see that more and more people are commuting to work. Now it's past 7 a.m., and the earthquake will be occurring soon. Okay, the earthquake has just struck. So on the right side, you can see how the lights gradually dissipate over time. Using the data we have, when we visualize it, insights like this become clear. However, simply receiving a dataset does not automatically allow us to conduct this kind of research. Compared to Tokyo, train stations in Kansai are built in such a way that people pass through the ticket gates more frequently. In the Kansai region, people often have to exit through a ticket gate when transferring trains. I believe that's becoming much less common in Tokyo. So for example, if someone takes the Hankyu line, then transfers to the subway and then rides the Kintetsu line to go somewhere, even if that entire journey is one trip to go to a certain destination, if each segment is treated separately, we cannot accurately capture their movement. Therefore, we've created a set of rules to carefully process the data on our end, connecting individual segments to reconstruct the complete trip. Specifically, when linking segments, if a person enters the next gate, within 30 minutes of exiting the previous one, we consider it part of the same trip. This also relates to the social context that I mentioned earlier. We consulted with railway company staff, and based on their input, we decided that a trip could be considered a single-purpose trip if the segments occur within 30 minutes of one another. The diagram shown here that compares Osaka and Kyoto uses this approach. So the Goza no Okuribi and Tenjin festivals are held in summer in Kyoto and Osaka. This diagram shows where festival goers are coming from by train for each of the festivals. Looking at Kyoto on the left, we can see that many visitors come from neighboring cities such as Nara, Osaka, and even Kobe to attend the festival. For the Tenjin festival on the right, I think it's evident on the diagram that there are visitors from Wakayama and Kobe, but visitors from Kyoto are not very noticeable. People from Osaka attend the Kyoto festival, but not the other way around. Why does this difference occur? Of course, trains run in both directions, and ticket prices are the same. So these factors don't explain the difference. As for the reason, Anyone with some knowledge of Kansai would probably think, that makes sense. It comes down to the difference in mindset and attitudes between Kyoto and Osaka residents. To understand the background that leads to differences like these, understanding the cultural context, as I mentioned earlier, is essential. Next, we process this data a bit to see what insights could be gained, and here are some examples. On this page, it says paired uses here, but it distinguishes trips made with friends or acquaintances from other kinds of trips. If you look at the diagram at the bottom on the left, this bottom left figure shows data for all users of that particular station. The upper figure indicates the number of people who used that particular station, when only considering the trips that were made with friends or acquaintances. So the bottom number is the total, and the top are only those moving in such pairs. You may notice faint vertical lines on the chart. These indicate days when events were held at venues near each station. This is called event detection. Looking at the lower diagram that shows the total number of users, this alone doesn't necessarily tell you whether an event is taking place. You can spot particularly large events, but when it's a medium-sized or smaller event, you can see that there isn't a big difference compared to a normal weekday. Looking at the upper diagram, if we focus only on those moving in pairs, I think you can all clearly see, just by looking at the diagram, the specific days when the events actually took place. On the right, we have an ROC curve of the data. The green curve represents only those that are moving in pairs. You can see that events are predicted with very high accuracy. In the dataset I mentioned earlier, there's no information included about whether trips are made with friends or acquaintances. Therefore, we developed a method to identify those trips, and using this method, you can see that the accuracy of event detection improved significantly. Later, at the end of the presentation, I'd like to give you the answer after your breakout sessions are over. But I'd like you to think about how we identified the trips in which the users were moving in pairs. What kind of process would let us identify these trips? I think you'll all get it if you give it a little bit of thought. I'll provide the answer at the end. I have a question for you all. The question is this. Men in their 60s, compared to women of the same age, tend to travel less often as a pair with friends in their 60s or with teens and people in their 20s, like their children or grandchildren. So then, who is actually riding the train with them? Many of you probably guessed this, but it's their spouse. Our data shows that women of the same generation in their 60s most often travel with them as pairs. The data doesn't actually show whether the person they travel with is their spouse, but socially, it's most likely their spouse. So for men in this age group, they are unfortunately not often accompanied by friends or children, but they are supported and cared for by their spouses. That is what we see. Next, I'd like to introduce some key methods that are used in computational social science. Among these, there's social network analysis and analyzing natural experiments on social media. What we do is extract insights from bibliographic and attribute data, then run simulations and gain additional insights from the results. It's also common to build predictive models using the data. Recently, as shown in the lower right, creating multiple AI agents and running virtual experiments has become increasingly popular, growing rapidly in use. From here, I'd like to briefly introduce 3 research results using these kinds of methods. Just a very simple overview. The first theme is about scientists' careers and computational social science. People sometimes have periods in their lives where they achieve consecutive success, often called a hot streak in English. This is often seen in sports or the arts, but it's also thought to occur among scientists. A famous example is Einstein in 1905, when he published 4 groundbreaking research results that came to define his career. A famous example, shown in the photo, is the mass-energy equivalence equation, which you've probably seen before. The average hot streak lasts about 3.7 years, and many researchers, during their careers, are said to experience it at least once. In the figure, you can see the hot streaks. The research results with a big circle indicate those that rank in the top 10% most impactful publications in scientists' lives or careers. In this figure, a hot streak is defined as a period of time in which, out of 5 papers that a researcher publishes in a row, if 3 of those papers rank in the top K%, typically 10% by impact, then that period is a hot streak. In our study, we looked into hot streaks to identify when they tend to occur and during which period of a researcher's career they tend to appear most often. If you look at the figure on the left, you can see the probability displayed in this diagram. It says K equals 3% here. This refers to a hot streak when a researcher produces a highly impactful paper that ranks in the top 3% of their work. If you look at this line, even if you change various conditions, it's clear that hot streaks happen most often at the start of a career. If you focus on cases like K equals 3% or 5%, which represent very high impact work within a researcher's career, we can see that hot streaks also appear frequently toward the later stages of their career. In that sense, I think this highlights how the beginning and final stages of a researcher's career are very important. We are also studying what the background factors are. And the beginning and final stage of a career have different characteristics. But at the beginning, strong relationships with a limited number of other researchers serve as a support. In the later stages of a career, it's understood that people are often supported by the large research teams they've built from the mid to later stages. Previously, it was thought that hot streaks for researchers occurred completely at random. In our study, however, we identified that's not the case, and that they happen more often at the beginning and at the end of a researcher's career. I think most of you are probably at the beginning of your career, so this current period can be considered an extremely important time in your respective careers. Next, I'd like to talk about human networks and computational social science. When it comes to research, each of you, of course, have your own research topic. But there are countries and universities that are advanced in that research topic, and others that aren't. So far, discussions on this topic have mostly been qualitative, and until now there has been no method to identify them objectively. In my laboratory, we wondered whether it'd be possible to identify this in a quantitative manner. I'll skip the details for now. But to quantify research topics, we looked at the papers published by each lab or research institute, as well as those published by each country, and examined the bundle of citations in those papers. We considered these citations to be topics. So, for example, if 1 million papers are published, and if each paper has an average of 100 citations, So multiply by 100 and it's 100 million. There are 100 million citations. We consider these 100 million citations to be topics. Regarding these topics, we can look at them by individual lab, by individual university, or even by country by aggregating all of the relevant topics. Today, I'd like us to take a look at the comparison between countries. So we take the research topics that have been aggregated in this way and calculate their similarity. In the process of indexing the similarities, we created an index called TPI for the calculation. What kind of indicator is TPI? For example, if the 2020 research topics from the University of Tokyo are most similar to the 2019 topics from the University of Oxford, then Tokyo is considered to be following after Oxford. And in this case, it's calculated to be 1 year behind. When you look at this by country, the results appear like this. The horizontal axis represents the progress in topics I just mentioned. Japan is located right here, slightly below at the center. Among the countries in the figure, it's located roughly in the middle. The countries on the left are those that are behind on topics. And the countries on the right are those that are ahead on topics. Countries that are ahead are shown in orange, and you can see that many of them are European or North American countries. At the top, you can see Hong Kong and Singapore sticking out. This shows that Hong Kong and Singapore are advanced in topics. The vertical axis shows the average number of citations. When looking at it by country, you can see that even after field adjustments, the more advanced the country is on topics, the higher the average number of citations. As expected, doing research that no one else in the world has done yet, or collaborating with researchers that conduct such pioneering research, is shown to lead to a higher impact. Unfortunately, Japan is right here around the middle, which I think shows that Japanese researchers need to conduct more ambitious research. This figure shows the background. And if you look at the figure on the right, the horizontal axis represents influential researchers. What we mean by influential researchers is shown on the left figure. This figure maps the global network of paper co-authorships, showing the connections among researchers. The USA is shown in the middle on the top row. The UK is on the top right, and Switzerland, China, and Japan are on the bottom row. The USA makes up a large volume of the global connections, and within the co-authorship network, it can be seen that it includes many researchers in the central area. The UK has a smaller volume of researchers compared to the USA, but you can see they're also located centrally. And for Switzerland, on the bottom left, they have a small number of researchers. But despite that, you can see that they're also located centrally in the network. In comparison, Japan and China are located more in the periphery. Looking again at the figure on the right, the horizontal axis shows the proportion of researchers who fall into the top 10% in terms of eigenvector centrality. The vertical is progress in topics. That's the index I mentioned earlier. This shows that there is a fairly high correlation between the two. Basically, what we can see in this global network is that countries with researchers in central positions have a tendency to be advanced in topics. Alternatively, the reverse trend can also be observed. As expected, in terms of the global research network, you can see just how important it is to be a part of the network and to actively participate within it. This is the last theme I'll talk about. IGO stands for Intergovernmental Organization. International organizations, unlike government bodies, actually write policy documents by citing a large amount of scientific evidence, including academic papers. They also create policies in this way. Within this process, the fields that appear most frequently are fields like medicine, health, the environment, and social science. Depending on the field, the distance to policy varies greatly. You can see on the right figure that environmental science is very close. That's the line on the top. The field that's relatively far away is physics. Today, as the main theme, I wanted to examine what kind of scientific evidence is sought by international organizations, as well as the types of evidence that are increasing, and this map shows what we calculated. As you can imagine, there are a large number of COVID-19 related works, with these works being cited often and increasing in number rapidly. Other than that, circular economy, data science, and AI, climate modeling. These areas have recently seen very high citation levels, as you can see in the chart. In terms of policy documents, what factors influence the number of citations that are used? The figure on the left shows what we found out. There are 4 factors: number of papers, journals whose published papers are frequently cited in policy documents, papers with references that are frequently cited in policy documents, and the author's previous citations in policy documents. I think these 4 factors explain the number of citations quite well. If you look at the figure on the right, I want you to look at the very right of the figure. But in terms of papers for which the author has been cited at least 64 times in policy documents, when that same author writes their next paper, there is nearly a 40% chance that paper will also be cited. In that sense, a very small number of authors are shown to have a strong influence on policies. For this next figure, I'll explain only the left side. But those authors are called policy influential scientists. What these scientists write is shown in light blue on the left, and everything else is shown in gray on the right. This is a calculation of how long it takes for a paper to be cited, and the vertical axis represents various fields. In any field, you can see that when policy influential scientists write papers, they're not only cited more widely, but are also cited more quickly. In other words, in this world, there exists a path connecting science and policy. And mediating that path and taking on the central role are a limited number of scientists. This research shows that framework clearly. It's similar to the research I just introduced. But I myself have experience being involved in global policy making in the past. For example, for the OECD, or for meetings related to APEC. Relating to policy influential scientists that I was talking about earlier, my own knowledge of cultural and social context has been useful for forming hypotheses, and in fact, it has proven helpful in advancing this kind of research. Lastly, I'd like to briefly talk about deep tech entrepreneurship that connects such engineering knowledge with society in concrete ways. I'm currently leading deep tech entrepreneurship education, which we run in both undergraduate and graduate programs. The characteristics are shown on the right, but we have this community called DICE, where we welcome the particularly enthusiastic students who are finished with their lectures. Currently, we have about 250 members. In communities like DICE, we provide support to students through activities like field studies, mentoring opportunities, and overseas training sessions. Regarding the lectures, a typical lecture has about 13 sessions, each lasting about 105 minutes. And at the end, there's usually a report or final exam. In the program I'm working on, The blue parts have been added. We believe networking to be crucial, so we start with a student gathering. Between the lectures, we have experts and former students provide support in various ways. For instance, mentoring or acting as someone to bounce ideas off of. In addition to that, we also visit actual labs and do fieldwork in the community. Finally, as I mentioned earlier, the particularly motivated students join the DICE community. And those students can receive support for 2 years after the program. Regarding this lecture, we conducted student surveys before and after the program. And looking at the results, this is a survey for undergraduate students. But you can see that their willingness to enter a master's or doctoral program increased by a significant amount. In these fields, instead of choosing between startup or research, there's a tendency for students to keep both paths in their purview as they make their career choices. Also, when it comes to deep tech, I've heard many people share how they've realized how important it was for them to have a deep understanding of deep tech once they start their entrepreneurship activities. In any case, activities like deep tech entrepreneurship and bringing these ideas and technologies to society, as well as the research related to it, are actually more present in our lives than people think, and I hope you realize that. Finally, starting in 2023, there's been a new initiative backed by our university president, involving study tours in Kenya. We've already held it 3 times, and this year 18 people participated. Then there's TICAD 9 held in August, where we're planning to have a side event where we'll give a presentation. I've touched on a lot up to this point. But even beyond just engineering, I'd like you all to enjoy what I like to call psychologically distant interactions between your own field of expertise and society. I'd like to conclude the presentation here.